This is Tech Math 2, which I managed to spell correctly the first time this time. And we're in section 9.8. And it has to do with using logarithmic equations to solve exponentials. So we have 3 rules, maybe 4. Yeah, we have 4 rules. So if we have money, then the amount of money I have is the principal I invested, 1 plus whatever the rate is, divided by the number of times a year that I compound the interest by, times the number of years I do it by that, times that number. So if I do this number and say I'm going to get 10% interest over 10 years, and I come up with a really cool number. When I was 27 years old, and I bought a variable life insurance policy, and that was back when Jimmy Carter was president and the interest rates were like 15%. It showed that I would have $1 million in cash value in that policy before my 60th birthday. How much is that policy worth today? $27,000. The interest rates never stayed that high. So projections like that are totally bogus. So to do this past a couple years gives you numbers that are probably going to be wrong. We can have growth. So if I got some grass growing in my yard, it's going to grow at some exponential rate. And the height of the grass is going to be whatever the grass was, times the rate of growth times t, times some amount of time. And depending on what the rate is, if the rate's in per hour, then the t would be hours. If the rate was per second, then it'd be in seconds. Then I have decay. So I got decay, and I got y is equal to a e to the minus rt. So these two guys come into play in electrical engineering because growth means I've got a capacitor and I'm charging it. That's growth. Well, not yet. No, it's not. Cancel that idea. We'll go with decay. Decay, I have a capacitor and I'm discharging it. All right, there we go. Growth, on the other hand, keeps on going like that forever and ever. So that's what growth is. But we have growth with a limit. Growth with limit. If I could spell with. So I turn the page and I find an equation, and a y is, thank you very much, pen, for making that extra mark, is a1 minus, the amount that I started with, 1 minus RT. And now I have some growth. I'm going to get as big as A. Well, that's my capacitor charging. When my capacitor charging, there's some maximum amount of charge I can have, and I'm going to have some growth until I get to there. So that's what all those are about. Now, each of these formulas come from chapter 29. And I'm pretty sure it's chapter 29. Because if I have 29, if I have the change in my amount, change in time, is going to equals to some rate times the original amount. And if I go in and separate variables, and I have change in A divided by A is equal to R dt, and I integrate both sides of the equation, I end up with natural log of A is equal to RT. I raise them as powers of E, and now I have A is equal to, there's also a plus constant of integration there. So it'd be the constant of integration e to the RT. And so that's where my growth equation comes. It comes right from differential equations that are sitting in chapter 29. But because we're in chapter 9, we take the results of those calculations and we use them in chapter 9. And then later on we go back and actually solve the original equation to get there. I'm sure no one wanted to know that, right? Anybody wanted to know that? Wyatt wanted to know it. I just feel that that's the case. That, yeah, I'm sure that that's the case. That Wyatt wanted to know it. Okay, so we'll do number 1, and so I've got $2,500, and I'm going to compound it quarterly at 7% interest. And I'm going to do that, okay, what am I supposed to do? How long? Okay, so this is equal to 4,500, and I want to know what t is. What is this, e to the RT? E to the 4t. And then t would be in years, because I'm doing it quarterly. I put a 4 up there. Now, I'm doing that from memory. I go back and I look, and yeah, that's what it is. Okay, excellent. So 4,500 divided by 2,500 is 1. Where's my calculator? In my pocket. What is it doing there? 0.045 divided by 4 equals 0.1875 e to the 4t. Okay, so I've got, what I got, 9 over 5? 9 over 5 divided by 1.01875 is equal to e to the 4t. There's my red pen. The 0 goes away, the 0 goes away, 5 goes into there 9 times, 5 goes into here 5 times. Fine. So 9 divided by 5 divided by 1.01875. Alright, so I've got 1.76687 is equal to e to the 4t. I'm going to take the natural log of both sides, and I'm going to get 4t is equal to natural log of my answer, 0.5692, and I find that t in years is going to be, how come that is so long, I wonder? I mean, that is just so completely wrong. 0.5692 divided by 4, 0.1, probably because I'm doing it in red ink. That would be my guess. You're thinking that's probably why it's all wrong. Alright. So I got a money problem. A is principal 1 plus rate over 4. Oh, gee. Okay. Where is Ben when we need him anyway? This is raised to the 4t. Not e to the 4t. Okay, so raised to the 4t. I take, okay, no, I can't do that. All right, so where's my big eraser? All right, so get everything out of here. Yeah, that's sort of like using the mob. You know, your money went up in negative years. You know. All right, so 9 over 5 is equal to 1.081875 to the 4t. Now I can either take the common log or the natural log of both sides. It doesn't matter as long as I do the same thing. So I'm going to take common log of both sides. No, I'm not. I'm going to take natural log of both sides. When I put it in my calculator, I'm going to use natural log. I'm just going to continue writing the problem this way. Is equal to 4t times log 1.01875. So 4t would be log 9.5 divided by log 1.01875, and then whatever that answer would be 4 times that. Okay, got it. T is equal to 4 times whatever that is up above. 4 times log of 9 over 5 divided by log 1.01875 times, not times, divided by 8, because it's supposed to be divided by 4, and I already multiplied by 4, and I knew to do that. 15.8 years. All right, finally. Okay, so 15.8 years to go from 2,500 to 4,500. I then want to know how long will it take to triple it. That seems a little long. No, it doesn't. No, that doesn't seem a little long. Okay. And the B part of the problem, we're going to triple it. We want to go to 7,500 is 2,500. 1 plus 0.075 divided by 4 raised to the 4t. And we want to find t in years. All right, well, I got 3. 3 is equal to 1.0, what was it before? 1875. That can't be 0. Yeah, it can be. 1875 raised to the 4t. So 4t is equal to log 3 divided by log 1.0175, and that implies that t is equal to log 3 divided by log, way to go Doug, lack of parentheses, log 3 parentheses divided by log 1.01718 1875 close parentheses divided by 4. 14.7 years. Okay, well, if this is 14.7 years, which I think is probably correct, how did we come up with 15 years when we're going to a smaller amount? That doesn't make any sense. So I'm going to do that again. Log 9 divided by 5 divided by log 1.01875 divided by 4. That's much better. Where's my red marker? 7.9 years. So when you're dealing with money, there's a rule of 88. Does anybody know the rule of 88? You ever hear the rule of 88? Maybe it's 86. I don't know. I'm going to use 88. Anyway, And the rule says that if you take 88 and divide it by your interest rate, multiply it. Yeah, multiply it. Multiply it by your interest rate. Now you're going to divide by your interest rate. Divide by your interest rate, you end up with the number of years to double your money. So if we have 88 and we divide it by 7.5, and you say, why didn't you divide it by 0.075? Well, because it's a stupid rule. Divided by 7.5, you'll see it takes 11.7 years to double. Yeah, I don't think it's 88. I think it's the rule of 86. I'm making up these rules as I go along. Rule of... Okay, well, cancel that rule because I forget what it is. Boom. All right, there we go. Got rid of that rule. All right, well, back to... But any financial advisor has a simple rule that'll tell you when you're going to double your money. Okay, I guess we'll use number 3. Rule of 76? Maybe it's the rule of 76. That doesn't work either. Yeah, 76 might work. Rule of 76 divided by 7.5, that's about 10 years. And we didn't double yet. Okay, well that might work. Okay. Number 3, I have 175 grams of some element, and I'm going to decay to 25 grams. How long will it take for 75 grams of an element to make 25 grams? And we have to go back to example 3 because they didn't bother to give us what we need. So example 3 says that the half-life of the element is 1.7 seconds. All right, so T 1/2 is 1.7 seconds. And the amount I have, so 25 is going to be equal to 175 times e to the 1.7 t. Minus. How long will it take? Okay, now minus 0.04 t because we're using that example. Okay. Well, if I have 175 grams, then in 1.7 seconds I'm going to have half that many, right? 175 divided by 2. I'm going to have 87.5 grams. And in another 1.7 seconds, I'm going to have half of that number divided by 2, 43.75. And in 1.7 more seconds, I'm going to have half of that number, 21 grams. So I expect my answer to be someplace less than 3 times 1.7, less than 5.1. So I expect my answer to be less than 5.1 seconds. All right, so here we go. 25 divided by 175 is equal to e to the minus 0.404 t. I take the log of both sides, natural log of both sides. So the natural log of 1 over 7 is equal to minus 0.04 t, and t is going to equal the log of 1 over 7 divided by minus 0.04. All right, so natural log of 1 divided by 7 divided by 0.04, and I end up with a number way too big. Way too big.
It's 0.4.
Oh, it's only 0.4?
Yeah.
Okay, well that would explain it. Alright, so we'll go back and change this to a 0.4, that to a 0.4, this to a 0.4, and we'll divide by a 0.4. Alright, log 1 divided by 7 divided by 0.4, and we end up with 4.86 seconds. 4.86 seconds, and we're expecting some number less than 1.5, so that's perfectly okay. We're happy with that number. All right, now back to what we're doing. We'll do threshold of pain next. Unless anybody want to do a chemistry problem, a pH problem? No, not particularly. Okay, so we'll do threshold of pain next. Number 13. So 120 dB is the threshold of pain, and we know that dB is 10 log my intensity divided by my intensity naught, and we're supposed to be solving for the intensity up there. Okay, and we remember, because it was just yesterday, dB is 10 log divided by D, and what I'm trying to get, that the intensity naught is 10 to the minus 16th watts per centimeter squared by convention. So if we're in watts per centimeter squared, we're going to use 10 to the minus 16th because that's the threshold of hearing. If we're going to use watts per meter squared, then we're going to use 10 to the minus 12th. But they want us to find the answer in watts per centimeter squared, so we're using 10 to the 16th. All right, so back to trying to do the calculation. 12 is equal to the log of the intensity, the answer I'm trying to find, divided by 10 to the minus 6. Okay, I'm going to raise these as powers of 10, and I'm going to have 10 to the 12th is equal to I divided by 10 to the minus 16, and then I'm going to cross multiply and say 10 to the minus 4th watts per centimeter squared is the threshold of pain. Threshold of pain. There we go. And of course, from The Princess Bride, we all understand where pain comes from, right? All right. No, we don't. We're culturally deprived. All right, so whatever. All right, well, that seems okay. Now we're down to 19 because this is an electronics program, and 19 is using one of our favorite words, current. So my current is 2.7 e to the minus 0.2 t. Find t in seconds when I is 0.35 amps. So 0.35 amps, 2.7 e to the minus 0.2 t, and we're solving for t. All right, well, 0.35 divided by 2.7 e to the minus 0.2 t. And we'll take the natural log of both sides, and we're going to have minus 0.2 t equals the natural log 0.35 divided by 2.7, and then we're going to say t is natural log 0.35 divided by 2.7 divided by 0.2, which is equal to, all right, now we're ready, log 0.35 divided by 2.7 close parentheses divided by 0.2 equals, and I'm going to have 10.2 seconds. 10.2 seconds. Then I'm going to come back up to the original problem and say second function numeric solve 0.35 equals 2.7 times e to the minus 0.4 times x. Okay, and I'm going to go and solve that for x, and I come up with 10.21. 10.21. What I have seconds, what I had before anyway. 10.2 seconds. Okay, so we'd probably round it off up to 10 seconds anyway, call that our final answer. Okay, so my calculator will solve that problem directly if I choose to remember that. Okay, next guy is a discharging problem. So obviously that is in rate 2. It has our favorite word current in it. And the discharge current of a capacitor, I is equal to 0.01 e to the minus 75 t. So that means that the time constant, RC, is 7.5, in case anybody was wondering. 7.5, and t is in seconds. Wow, that's pretty bad. Okay, find t in seconds when I 0.004 is equal to 0.01 e to the minus 75 t. Right? And because we have to show math every now and then, we'll go and divide both sides. 0.04 is equal to e to the minus 75 t. Natural log of both sides. T is equal to natural log 0.4 divided by minus 75. It's a natural log, if I can find natural log, which I can't because I'm still in my other thing. Natural log of 0.4 divided by minus 75 equals, now why would they want it in seconds? I would put down 12 milliseconds is what I would do. Well, that is in seconds, right? Milliseconds is in seconds. No, probably not. 0.012 seconds. Okay, there we go. I did that. We're going to go back to the top of the problem again and see whether or not my glorious calculator can solve it for me. 0.004 equals 0.01 times e to the minus 75x, solve for x, and da 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 da. Obviously I'm having it solve around 10, which was a stupid thing. I should have had it solve around like 1. Well, the calculator is still thinking about it. And we're going to quit that, and then we're going to do it again. So I got the same problem, but this time we're going to solve around 0.015. There, that's better guess. There we go. 0.01227271720. So yeah, the calculator is going to give you that answer. So that's pretty cool. Number 21. The formula for instantaneous current I at time t in milliseconds is given by this formula. I really don't think so. Where E is the voltage, R is resistance, C is capacitance, farads are that. Okay, find T. Okay, so I've got 3.91 times 10 to the minus 5 is equal to 100 to 3 significant digits divided by R 2.00 times 10 to the fourth. Now why would I write it that way? I'd write 20K. So I wouldn't write it that way. So I'm not gonna. 20.0 K ohms. Now we know that that can't be right. You're not going to have 3 significant digits in your resistor, and you really paid a lot of money for it. E to the minus T divided by, is that a divide by? RC. 20 kilo ohms times 2 10 to the minus 8 farads. And I wouldn't write it that way either. But I ran out of room, so I can't write it right. And I can't put a bracket because I ran out of room for bracket. Okay. We need everything on the other side of the equation. So 3.91 double E minus 5. As I was saying, 3.91 double E minus 5 times 20 double E 3 divided by 100. All right. So I got 7.82 times 10 to the minus 3 equals E to the minus T divided by, now we know this formula is wrong. We should, we'll just use it, doesn't matter. 20 double E 3 times 2 double E minus 8. 0.0004. Okay, we'll take the natural log of both sides of the equation. And we got minus T over 0.0004 is equal to the natural log of 7.82, 10 to the minus 3. And we have T equals natural log 7.82 times 10 to the minus plus 3. Is it plus 3? Minus 3. Minus 3, minus 3. Divided by minus 0.0004. T is equal to. Oh, this is an odd problem. That's bad news. If I don't get it right, everybody will know it. 7.82 double E minus 3 divided by 0.0004 with a minus sign in front of it. That seems hard to believe. Oh, well, this is in milliseconds. So that'd be 12.1 seconds. Let's see what the author thinks. 898. Here's chapter 19. Chapter 11. Chapter 9, 8. What problem is this anyway? 21? Oh, bummer. 1.9 times 10 to the minus 3 milliseconds? Wow, talk about being the wrong side of the problem. All right. Luckily, I can't see the whole problem, so there's no way I can figure out what's right. Anyway, back to here. Okay, I entered that right. I got that right. I got that right. I got minus T. And there, that is a divide sign there, right? Divided by this guy. All right, so that looks good. Divide by this guy. Well, you know, when I get to here, and I take that and I divide him, I'm supposed to be multiplying, right? So that's the problem. All right, so now that we've established what the problem is, now we can redo it. All right, so T is equal to natural log 7.82 10 to the minus 3 times minus 0.0004. Okay, well, we can recuperate that in our calculator. We can just go times 0.0004 squared and come up with 1.94 milliseconds. Is that what I'm supposed to get? 0.194 milliseconds. Huh? We don't remember? .194 milliseconds. 9.8. Yep, very good. Nope. Nope, that's not what I'm supposed to get. It's in milliseconds. Alright, so t is in milliseconds, so I gotta call this 10 to the minus 3 milliseconds. Now the author and I agree. Okay, well, isn't that? Or at least one of the graduate students agree with me. So now the issue is, I've got this radioactive material over here. It's 1 pound. And I got this radioactive material over here, and it's 1 pound. This guy's got a half-life of 10 minutes. And this guy's has a half-life of 10 years. Which one do I want to hang out with? Well, neither of them, obviously, but that'd be one answer. Which one would I want to hang out with?
Probably the 10-minute one.
So that's exactly right, Nate. You want to hang out with the 10-year guy, because this guy's going to irradiate the heck out of you and kill you.
Oh, okay.
Because he's going to decay to half of the 10 pounds to a half pound of stuff in 10 minutes. And if you're hanging out when that's happening, you're going to be dead. Whereas this guy you can have in your back pocket and put up on the shelf at night and take it to work with you. It really isn't going to matter because it's going to take 10 years before it can do much to you at all. So yeah. So the guy Cobalt-60 is the guy we worry a lot about. Cobalt-60 has a half-life of 6 years, but it puts out 2 gamma rays that are 2.5 million electron volts and is very damaging. And so when the itty bitty bit of this got recycled in Mexico once in a steel supply, they ended up making tables and sending them out to the community, and people started getting sick because you can't hang out with that stuff very, very often. But so the good news is that in about 2 weeks, most of the radioactive stuff is going to decay away from a nuclear weapon blast. So that being the case, that's when you made your bomb shelters back in the 50s and 60s. You always stacked them for 2 weeks of food, because after 2 weeks you could come out and starve. I mean, you come out and not be irradiated bad enough. So your body is taking a certain amount of radiation every year from the sun, and is healing itself constantly, or not. But you don't want a whole lot at the same time because your body can't handle that. Okay, well, let's see. Let's do number 23. In my generation, we spent a lot of time in our school system discussing things like that because it seemed very imminent. V1 minus e to the minus t over RC. All right, so that's what we got. Find t in milliseconds. R is what? 2 mega ohms. All right, well, first of all, we're going to find RC. RC, I have 2 meg times 4 microfarads. All right, so that'd be 8. RC is going to be 8. Okay, well, that's good. 8 seconds. I want to know the time. Okay, so when I have 75 on my capacitor and I'm heading up to 100, how long did it take for that to happen? E to the minus t over 8. All right, well, that looks good. All right, so this goes on the other side. 3 over 4 is 1 minus e to the minus t over 8. Bring the minus 1 on the other side. Minus 1/4 is equal to minus e to the minus t over 8. And my minus signs now go away because I have a minus on both sides. I can't take the natural log of a negative number, so that's why that has to happen. But now that they've gone away, now I can take the natural log of both sides and say natural log of 1/4 is equal to minus t over 8. And then t becomes natural log of 1/4 times minus 8. Natural log. Where's my odd button? Natural log of 0.75 times 8. And it looks like I've got 11.09. And that would be in seconds. And I want the answer to be in microseconds. So it looks like I would call it 11. 11? Do I have 3 significant digits? Yes, I do. 11.1 times 10 to the 3rd milliseconds. And I could look in the back of the book, but I'm not going to bother. Well, one more problem, number 24. Oh, wait a minute, I got to do 28. All right, 28. A 50-gram sample of radioactive radium decays at the rate of, so 28. So I got the natural log of the amount is minus, that's a minus sign, minus the natural log of the 50 is equal to k times t. Okay, it does that, okay. Where a is the amount, t is the time in years, and k is a constant, which I already know. Okay, so natural log of a minus the natural log of 50 is equal to minus 4.1 10 to the minus 4t. Okay, I got that. Find the amount remaining after 225 years. Okay, so 25 years. So the natural log of a minus the natural log of 50 is equal to 25. 4.1 times, well, 4.1 double E minus 4 times 25. All right, so I got 0.01025. Really? Yeah, I guess I do. With a minus sign. All right, so the natural log of a, and that's what we're trying to find the amount left over, it's going to be minus 0.0121025 plus the natural log of 50. Natural log 50, 3.912. And so natural log of a is equal to 3.512 minus 0.01025. 3.90177. So I raise these as powers of e, and I get a is equal to, so e raised to the answer gives me 49.49 milligrams. Milligrams. Okay, so I'm not losing very much. Not going to lose very much at all. That was 28. Excellent choice. Can't look in the back of the book and know it's the right answer. But something with a K of 4.1 double E minus 4 is going to have a half-life of 2,439 years. So my half-life, T1/2, is going to be 1 over K. So my half-life for this thing is 22,440 years. So after 25 years, I'm not going to have very much decay away. That's not going to happen to me. Well, that begs the. Now we used to do one that had to do with. That's probably later on. Has to do with carbon-14 dating. So we have all of 3 minutes, 2 minutes. Let's talk about carbon-14 dating. So how do I get carbon-14? Carbon-14 has a half-life of, I don't know what it is, but it's not very long. It's like maybe 10,000 years or so. So how, if the Earth is 4.8 billion years old, how can there be any carbon-14 on the Earth? Okay, so obviously there had to be some method to get it here, right? So carbon-14 is produced by the sun. So carbon-14 is produced by the sun and is in some equilibrium amount when some plant grows. So here I got some plant. It's growing. And and it grew 10,000 years ago. So, and so I got that equilibrium amount is in the plant, and then when the plant dies, it quits absorbing it, it now decays, and now by the amount of carbon-14 left over, I know how old it is. Okay, so that's the carbon-14 dating method. Now, that works perfect if the Earth is 4.8 billion years old, right? However, what if the creation guys are correct and the Earth is only like 900,000 years old? And when it was created with some equilibrium amount that we don't know what it is, then all this carbon dating is wrong. Okay, so the religious right would argue that carbon dating is not going to give you the right age because your assumption that the Earth is 4.8 billion years old is wrong, and therefore you can't use carbon dating to come up with the age of some artifact that you came up with, because you don't know the equilibrium amount when God created the heavens and the earth. Okay. So that's just one of those interesting arguments that you'll come across every now and then. And it's politics, it's not science. So your opinion, one way or the other, is perfect. Unless you're the CEO of a major company, then you could be fired for an opinion, right? Yeah. So that could happen too.